can't see it. What is it? 6. R is 5. I'm going to go through this kind of quick because we did one like this yesterday. I'm using the geometric sequence formula. Come on now. So 4, 6, 8, 7, 5, 0 equals my first number, which is 6, times my common ratio, which is 5 to the power of n minus 1. Okay? Divide everything through by 6. If we use one side, do the other, because we're trying to solve for n. Now you can solve this with logarithms if you want. Not necessary. 468,750 divided by 6. Somebody help me out. 78,125. Good news is, look at those last two digits at 125. If it ends in 25, that means it's going to be a power of 5. What power does a 5? I don't know. Go to Desmos. Yeah, look, it's 5 to the 7th power. Figured it out right there. Okay. But you can do like a guess and check until you find it if you needed to. So that's 5 to the 7th power. And when my bases are the same, I can make my exponents the same. Now, if I didn't recognize this, I could solve this with logarithms, but I think that's a little extra work that you don't need to do. So if n minus 1 is equal to 7, what do you subtract from 1 to get to 7? And that is 8. So that means this is 8, and now, and only now, can I use my formula. The sum of my first 8 terms, which I just determined, I'm looking at 8, is equal to, now my first number, which is 6, parentheses, 1 minus r, which is 5, to the power of 8, all over 1 minus 5. And if I plug that into Desmos, I end up with 585,936. 585,986. Okay, this is like the one we did yesterday. Okay, the next one's a word problem. So work it out so that you, again, the key is you need to figure out what A is, you need to figure out what R is, and you need to figure out what N is. And the nice thing on the word problem, you don't have to calculate N, it is given to you. You just have to pull out the numbers from the words. Go for it. Try the next one. So this one's a little more straightforward. A sub 1 is 3. Only thing that is ever so slightly amount of work is change 60% into 0.6. Okay. So your common ratio is 0.6 here. Okay. And then it tells how many times after the 10th row. And 3 over 5 is fine too. Yep. Okay. So S sub 10 equals fraction bar. A1, which is 3. 1 minus 0.6 raised to the power of 10. All over 1 minus 0.6. Control A, Control C, Control V. I think I did this already. No, I did not. So 7.45 feet is the total distance it traveled over all 10 throws. Okay. Double squiggly because approximately equal to 7.45 backslash feeties. Protons. Okay, open up 8.5 when you're done. We're going to talk about this thing called sigma notation.
Is this a long lesson?
No. So this last lesson, nothing is really new. What we're going to use is a slightly different notation and talk about something that is called partial sums. It'll make more sense when we look at it. Okay. All right, sigma notation. So take a moment. We're going to be answering these two questions. How is sigma notation used to evaluate series, and what must be true to find the sum of an infinite sequence? Okay, so just take a look at the notation for a moment. It looks worse than it is. All this is K equals 1 is a sub 1. This is the subscript. Upper limit means we're going to start here and finish there. That's all. The argument for right now, our arguments, Ahmad and Caleb, will be either arithmetic or geometric sequences. That's it. Okay, so we're going to use the explicit rule for either one of those. So if we write this, this is really showing a1 plus a2 plus a sub n. We've done this. Sum up. That's it. So it's really every time you use sigma notation, it is either the sum of an arithmetic or geometric sequence.
So would the lower limit be a1? Or?
Most of the time. We'll get to that. Okay. In this particular case, this is exactly what it would be. So we're going to convert this series into sigma notation. How will I ever be able to do that? I don't know. Click over here, go to the 5th row down, right down in the middle, and there it is. Okay. Little sigma with an I in it. There we go. So you'll see a gray box on the bottom and a gray box on the top. This tells you where to start and where to finish. I am going to utilize the same symbols they have, and so instead of starting with I equals, N equals. Or, I'm sorry, instead of starting with N equals, I equals. Ahmad, go sit up here behind Jared. That's not working for me right there. Okay. So I equals 1. And then you count how many terms there are. I got 1, 2, 3, 4, 5, 6, 7. So my top number is 7. Okay? And then I have to figure out the explicit rule for this sequence. So I'm looking over at my arithmetic explicit rule, which we haven't done for a few days. I'm still in my equation. Okay, my first term is 3. Add, what is my common difference from 3 to 7 to 15 to 17 to 19 to 23? 4. So plus 4 times n minus 1. That's it. So this is what this is written differently. And then if we simplify this, let's go ahead and do that. So equals, using that sigma notation, from I equals 1 to 7, and then simplify. So 3 minus 4 is negative 1 plus 4n. So instead of writing all of this out, the 3 plus the 7 plus 11 plus the 15 plus the 17 plus the 19 plus the 23, another way. That's all. Okay. So it's just a different notation. Because there's 1, 2, 3, 4, 5, 6, 7 terms. So the number on the bottom tells you where to start, and the number on the top still tells you where to end. Unless stated otherwise, you can assume start with the 1. Not always, unless stated otherwise, which is going to happen in the not too distant future. All right. So let's go ahead and calculate this. What kind of series is this? What do you think? Look up. Arithmetic or geometric? It's arithmetic, so we're going to use the sum formula. Okay, so if I'm right here, that's the same as S sub 15 equals. So I need to know how many terms do I have? Top number tells me I got 15. I need to know what my first term is. It is not 1. Okay, because 1 is what I plug in here. So 1 minus 1 is 0. 10 times 0 is 0. 0 plus 500 is 500. So my first term is 500. Okay, I am going to do a little bit of work down here. This is not geometric. Okay, we'll see the difference. Look at the difference between arithmetic and geometric up there on the sideboard. Okay, so to find my 15th term, because I need my last one, it equals my first one, plus my difference each time is 10, and I have to multiply that 14 times. So 14 times 10 is 140, plus 500 is 640. I come back up here, I add 640, and I'm always dividing by, look over there on the sideboard, Arithmetic series is always divided by 2. Okay. So I will just take this little piece right here, copy, paste into Decimos. I'm just going to clear the board. So if I add up all those terms, I get 8,550. Not approximately, exactly equal to. Okay, that's it. So instead of using the words, if my first number is 500 and my common difference is 10, find the sum of the first 15 numbers. This is how you would do it. Okay. Better, Dylan? Okay. Questions? Ready? Hey, Quan, is that an arithmetic series?
No. Geometric.
It's geometric. How can I tell? Where's the variable?
Oh, I see. Exponent.
And the exponent. So use the sum for a geometric series. Did you got it, Ahmad? You got a question? Your computer. That's lovely. So click authorize. And then go from there. Okay. So this time, come on now, there we go. So S sub 5, I'm only looking at 5 terms, equals fraction bar. I'm looking at my other formula, A sub 1 times 1 minus r to the n over 1 minus r. So my first number, again, plug in 1. 1 minus 1 is 0, but 0.95 to 0.95 to 0 is 1, and 1 times 8 is 8. So my first number is 8. Do I need my last number like I did last time? Nope. But I do need to know my common ratio. Yeah, look at that. It's really nice. It's right here in a parentheses, 0.95. Doing this 5 times. On the bottom is 1 minus 0.95. So if I add up the numbers 8 plus 8 times 0.95 plus 8 times 0.95 squared plus 8 times 0.95 to, got the idea? To the 4th power, then that's going to be my answer. Okay. So just take this little piece right here, and we've got 2 decimals, so we're going to round it to 2 decimals. Go to Decimos, paste. So 36.195 round to 36.2. This time we use our double squiggly. Come on. Up and away with 2 stencil decay. Ah, right, not that one. This one over here. What was it? 3 point what?
36.2.
36.2. Thank you. Done. Okay. For this test, the only type of series we're looking at is arithmetic and geometric. For the ACT, and we'll practice that a little bit more when we come to it, it might be different. But at least for this test, arithmetic and geometric. Got it? Kind of, sort of. Is it new stuff?
No.
Is it new notation? Yeah. Okay. All right. So if I give you an arithmetic sequence, am I starting with the first term here? Well, no, we're starting with the 4th term, but I give him the first 3 terms. So I have a couple choices. I can use the fancy formula that if I'm going from the 4th term, I need the 4th term, the 5th term, the 6th term, and the 7th term. That's only 4 numbers. Do you want to use the fancy formula for 4 numbers? Okay. So notice we're not starting with 1. Okay. Normally I'd have you guys do more of this, but in the interest of time, nope, not you. Oh, come on now. Fine. Okay. Fine. Fine. Too many crickets. Okay. So I just want to come down here. So I need to find my 4 terms. What's my common difference? They're going down, so it's got to be -5. Okay. So find your 4 terms and add them up.
Our 4th term is
There you go. -7. What's my fifth term? Scott? -12. Hey, shouldn't I be adding these? Yeah, let's put a plus sign in between these. What is my sixth term? Torah? Okay, help her out there, AGNR. Yep. Negative what? -17. And my seventh and last term. How about it, Brianna Mendoza? Last one? Not sure. Brianna B? Exactly -22. Okay, so let's go through this. Oops, there's too many negatives. All right, so I'm at 8. I go down to subtract 5. I subtract 5 again. With me so far, Torah? So I subtract 5 again. -2 minus 5 is -7. That's how Artemis came up with that one. And then Scott said, I'm going to subtract 5 again. That's -12. Okay? Then we subtract 5 again and subtract 5 again. So you're just subtracting 5 and 5 and 5 and 5. Okay? So to find the sum of these, I know the answer has to be negative because they're all negatives. So let's see. 12 and 7 is 19, 36, 58. That's it. -58.
I got that too.
Okay. Is there another way to do this? Yes. Will I show it to you in a few minutes? Yes. All right.
Is it easier?
Well, it's easier when the numbers are further apart. So if I say find the sum of the numbers from 4 to 26 or 14 to 26, you really want to add up the 14th, the 15th, the 16th. Yeah, so then it's easier. But when there's only a few, I would just do it this way. All right, given the geometric sequence, you're finding the sum of the first 8 terms. Again, judgment call. How much work is it for you to find the next 5 numbers, or do you want to use the formula? But if you're going to use the formula, you have to calculate, well, what is A1, what is R, and what is N? So take a few moments and find the sum of the first 8 terms of this geometric sequence. We're not recording anything. Poop. Okay. These text boxes are driving me cray-cray. But I have figured out a way not to deal with them anymore. Okay, so R equals 80 divided by 100, which should equal 64 divided by 80, which equals what when you simplify? A smaller fraction. Let's take a fraction this time. Told a lot of decimals. 80 over 100 is 8 over 10, which is 4 over 5. Okay, so that's my common ratio. So we're looking at a geometric series. I'm only starting with my 4th term. Okay, now this one you can still do by hand. I would not use the formula because, again, I only need 4 terms, but this one's going to take a little bit more work to write. So 64, let's use the equation editor because we're going to want to do this. Calculate this in Desmos. 64 times 4/5. That is my 4th term. Plus 64 times 4, well, let's do some parentheses. Times 4/5 squared. And since I don't want to have to retype stuff, watch this. Okay? Let's see if it's going to work. I don't think it's going to work. I don't think it's going to work. I don't think it's going to work. I'm going to try it. Well, remember, Kimmy doesn't like stuff in here. So let's see. Copy.
Yeah, don't worry.
Paste. So.
No.
Does the HTML. Okay, so watch this. Oh, just undo. Undo. Okay, so let's put that 2 up there. So what we're going to do is we're going to stop here and copy and paste into Desmos, and then we'll do the rest of it. Okay, so 2. Control A, Control C. This time it should work, hopefully. Okay, paste. Okay, that works. Now we can copy and paste to get the rest of it. So that's 4th, 5th. How many more do we need to do to go to 7?
5,
2 more. 5th. Wait, this was 5th. 5th, 6th, right? No, my brain not hurting. 4th, 5th, 6th, 7th,
Yeah, two.
Two more. I was right.
Yeah.
Jedi mind tricks don't work on me.
What?
So
Almost did.
almost did, yeah, it did. But then mathematics prevailed. Okay. Paste, and then change the 2 to a 3. Go down, paste again. Change the 2 to a 4. And there we go. Okay. So that's my 4th, 5th, 6th, and 7th term. So 151. Oh, let's just. Oh, we can make it a fraction? Look at that. 94,465.
No, I want this.
You can put the decimal in. I'm not going to be. So on the test, I'll be more specific. But I like fractions. Fractions are my friends. Okay, so I'm just going to put the sum. Sum down here won't let me do that.
Enter.
Enter.
So S, no, we'll just put it over here. There we go. Equals, bam. Oh, what happened? I like that. So we'll go old school. Ready? /625. And 2 different font types. Yeah, that's what drives my wife crazy. It drives me a little crazy too, but it's okay. All right. Wait. 94464
Yeah, wait, never mind.
or 94,464 625.
So you don't have to add 180 and 61.
No, because we're not starting with the first 3. We're not starting with 4.
Oh, okay. Thank
Okay.
you.
So this is what's known as a partial sum. So we're going to talk about that in a little more detail right now. So we're going to skip this stuff. Skip. All right. Couple things. Before we talk about partial sums, talk about the difference between convergent and divergent series. Okay. If you look over on the sideboard, you will notice something. I have the word infinite. I'm looking at arithmetic. So an infinite arithmetic series has no sum because it goes on forever. An infinite geometric series has no sum unless my common ratio is between -1 and 1. The reason is as follows. I'm just going to kind of write it up here with a drawing. So I got my formula, right? A1, 1 minus r to the n over 1 minus r. But if r is a fraction, and I take it to a really, really big number, so pick a number that's a fraction between 0 and 1, Caleb. Huh? 1/2. Okay, so go to Desmos. Let's clear off the rest of this. We don't need it anymore. And type in parentheses, 1/2. In parentheses, not outside parentheses. Okay. Fill in. Pick a really big number. 1,000. Hey, take a look. 1/2 to the 1,000 power, which isn't even close to infinity, gives me 9.33 times 10 to the -302, which means I've got more than 300 zeros after a decimal place, and then I'm talking about my first number. With something with 300 zeros, what is that really, really close to? 0. So if I take a look here, this becomes nothing because it's 1 minus 0. What's 1 minus 0?
0.
No. 1. And then 1 times a. And that's why we have the new formula. But the new formula only works when r is between -1 and 1, but doesn't include 0 because 0 wouldn't be a ratio. Okay. All right. So every sum that we've been looking at is really a partial sum of an infinite series. Say that one more time. Every sum that we've looked at is really a partial sum of an infinite series because we could go to infinity, but we don't normally. So the 6th partial sum, and you're going to see this phrase from time to time, of this infinite series starts with my first one and ends with my 6th one. Okay? There's my first term, second, third, fourth, 5th, 6th, and we add them all up at 78. Okay? So when I first taught this to you, isn't this a little easier? Okay, so this is why I taught this to you first. But you need to be aware of this sigma notation. Those of you that go on into anything with math or science, you're going to see this. Okay, there's actually infinite series that converge to like numbers like pi and e. That's a good question. It's kind of cool.
What's your
All right. So, ready? Here we go. If I'm starting at 5 and going to 18, this was Marco's question early. Well, how else could I do this? So pay close attention. I'm still using the same formula I did before. Okay? So the n times 8, 1 plus the last term. But what I'm going to do is I'm first going to go from 1 to 18. So I'm going to find the sum of my first 18 numbers. And then I'm going to find the sum of the first 4 numbers. And that will give me the sum of the numbers from 5 to 18. Okay, so I'm subtracting off the little bitty piece of the beginning. So instead of doing the 5th, 6th, 7th, 8th, 9th, 10th, 11th, 12th, 13th, 14th, 15th, 16th, 17th, and 18th number and adding them all up, that's a lot of work. Just use the formula. Okay, so the sum of the... So what did I have to do first? I had to find my first number, I had to find my 4th number, and I had to find my 18th number. And then I can use my formulas. Okay, so that's my sum of my first 4 is 62. The sum of all 18 is 657. So to find the sum of the 5th through the 18th is 657 minus 662 or 595. Okay, you're not going to see a lot of this on the test. But juniors, guess where segmentation is going to show up?
ACT.
So that's why I'm hitting this. I'm not doing this with the core classes because it's a little too much for them. Okay. And this is like a 2-day thing that we're doing like in a day because you guys are smart. We can get through this. Okay. All right. Can I have partial sums of geometric series? Yes, it's still done the same way. Okay. And then here is, I just think this is kind of cool. That if you have a series that goes on forever, it still has a convergent number. Got that, Matthew? Series that goes on forever, but still gets one number. So let's take a look at this. We're starting with what number? 90. Okay, so I'm going to use my formula right here. So the sum, so I'm going to use my special characters. What's my subscript if this is an infinite number of numbers? Infinity. So you have to go up to the top palette. Equals fraction bar. My first number is 90 because when I put a 1 in here, 1/10 to the 0 power is 0. Over 1 minus, what is my common ratio? Give you a hint. Look in the parentheses. 1/10. Okay. So that's equal to 90 divided by 9/10 because 1 minus 1/10 is 9/10. And we're going to go old school and change this into 90 divided by with old school division. Why am I changing old school division? What did you learn way back in elementary school? You can change division into multiplication and flip the second number because it's a reciprocal. Because division is really the inverse of multiplication. So 90 times 10/9. What happens to my 9? Divides into 90 how many times? 10. 10 times 10 is... So even though this series goes on forever and ever and ever and ever, your hand would fall off, you would die of thirst or hunger before you ever finish writing the series, the answer is just 100. You don't have to get all of the numbers. Okay?
Wait, where did you get the 9 over 10?
Because 1 is 10/10.
Oh, okay.
10/10 minus 1/10 is 9/10. Okay? All right. So I want you to find the 9th partial sum, which is really just find the sum of the first 9 terms. I don't care if you use the formula or find the first 9 terms or add them. Okay? And then after that, find the 11th partial sum of this one. This one you probably want to use the formula for. Okay? Because these numbers are going to get rather large quickly. When you have a common ratio bigger than 2, yeah, it's big. Okay? So see what you can do with those 2 on your own. And then that's it. So we'll go over them in a couple minutes.